Hello everyone, welcome to today's math chapter. It's going to be given by Saptarshi Halder, who is a M.Math student at ISI Banga. Interest analysis, and the topic is going to be on Besicovitch Covering Theorem. Over to Saptarshi.
Yeah, thank you for coming here this math talk. So today I am going to tell about Besicovitch Covering Theorem to a geometrical. I will not make it too much technical to understand. I will keep it as some basic geometry stuff and some metric spaces. So first of all, I want to start with some introductory measure theory, because otherwise I will not explain what motivates to study this Besicovitch Covering Theorem. So let's start with basic measure. So we have a set X, okay, and we have a sigma algebra sigma. So what is sigma algebra? We will see that. Sigma algebra, and we have a measure view. We call it measure. So the sets actually which is measurable, these are the this collection that collection of those sets is forms the sigma algebra. So what the property of the sigma algebra enjoys, that whenever a set belongs to a sigma algebra, its complement automatically belong to sigma algebra, and countable union will be inside sigma algebra, and the whole set is in sigma. So that implies the empty set is always in sigma. Right. So this is we have. So we now define mu. So what is mu? Mu is a function. Its name is measure. So it's a function from this sigma algebra. Into so and it has some property that mu of the empty set is equal to 0, and mu of the disjoint sets is just the sum. So where so what is the we mean? So an easy observation is that this is a subset of the power set of X. Okay. Take all possible subsets of X, but it is a shorter collection on which this sigma acts. So this is the domain set, and it enjoys these two properties. So EJs are disjoint collections, right? Disjoint sets. Okay. So this is the basic definition of measure, that mu, and we call X, this M, this is the sigma algebra, and this is the measure space. This is a measure space. Okay. So one can understand immediately from this definition, first of observation, that for a subset of B, that will readily imply that. Okay. So this is the monotonicity of measure. You can prove it using this. And for the second one, I want to say that it has this equality, but sometimes we don't need this equality to say that this whole one way inequality is sufficient for us. So what is this is I is 1 to infinity. This is called Savage. So these are two initial observations regarding measure measure we can draw. Now let's move forward, but here we have that abstract set X. Okay, we don't know what is this, but to do for today's talk, I need that set X to be first of all we take R and then it will be Rn. So there we introduce a term that modal measure on R. Okay. So what is modal measure on R? Modal measure is nothing but the measure which has that modal sets to be measured. Okay. So what are the modal sets? So modal sets. So the modal sets are basically the which generated by the open intervals. So what are the open intervals in R? You can readily figure out these are this type of. So this is the modal measure. So how we characterize this modal measure? Basically this is a length function. So mu of this, when mu is the modal measure, mu of this will be the just length of the input, which is bi minus a. So this is the thing for the modal measure on R. Now this collection is called the sigma algebra. So it always has a sigma algebra. Whenever we take a measure space, we have a sigma algebra. That sigma algebra is called the modal sigma. Okay. Good. Now we study. We just define the Lebesgue measure. So what is the Lebesgue measure? It has on R. What we have that mu of E is of course subset of R, right? So mu of E is infimum of this. Yeah. And such that this E is covered inside. Basically the Lebesgue measure on R. So what we are doing, that we are taking something like a power of the set E, and we are using this thing mu of ai of this set, flow open set. So what is this? It is basically the length. Okay, and take and sum it up and take it infinite. So we are telling that this is the Lebesgue measure what we have for of this set E. Okay, of course it's a subset of R, right? Now a generalization can come. So for Rn, what it was just a one-dimensional thing, right? It is just on the line. Okay, but whenever it is Rn, so it is changing its dimension. It is increased by some dimension. So where we are enclosing it like this, we will try to enclose this our subset of Rn, maybe that is some A, by n-dimensional some object. Okay, n-dimensional object, like a cuboid. So in that case, volume, but it's not necessarily three-dimensional. It may be higher. But how do we define the volume? Just multiply each of the length of each of the edges. Okay, it's different direction. Okay. So that is the Lebesgue measure for R. Now we suddenly move forward, and one observation one can make that is the Lebesgue measurable, those things is exactly same as Borel measure, but we can prove that it is not. We can have the examples for which it is Lebesgue measurable but not Borel measurable. We can have the example. So it is a finer description, but I will not go into it. Now I tell when do we call a set to be measurable? Maybe Lebesgue measurable. So a subset E of R is Lebesgue measurable if mu of P is equals to mu of condition will hold for all T subset of R, we tell that this E, set E is Lebesgue measurable. So this is the condition for being a Lebesgue measurable. Now we move forward, and one observation, maybe two observations I will tell, but before that I give three definitions which will be encountered in later on our talk. First of all, that definition. So mu, a measure on X, is regular. Remember the term regular if for each set A subset of X there exists a mu measurable set B such that this and so when we call this measure to be regular, that for each set X A, the subset of X, there exists a mu measurable set B. So I have told you that what is the definition of mu measurability. So B mu measurable such that A is a subset of B and this equality holds. Mu A is equal to B. So this is the thing for regular. Now we move forward. Definition 2. So mu on Rn. So where I have defined those Borel-Lebesgue things, remember on the real line, and we have extended into Rn. So in this Borel regular definition, we have that mu, here it is X, any set X, but here we will define that mu on Rn. Okay. Mu on Rn is Borel regular if mu is a Borel measure, mu is Borel, and this thing for each set A X there exists a Borel measurable set B such that A is subset of B and mu A equal to mu B. So this is the definition of Borel regular. So for Borel regular, the measure should be Borel. Otherwise, what is the meaning of this on Rn, right? It should be Borel, and then it will mimic the same definition as regular, but the set we are getting, that B, it was just a mu measurable set, but here it is, the mu is Borel. So what will be B? It is Borel measurable set. So we guarantee the existence of a Borel measurable set B such that this criteria A is a subset of B. This is the Borel regular thing. Now we give the definition of Radon regular. A measure on measure mu on Rn is called radon. If mu is Borel regular and for all K compact, okay, it is Borel regular. The mu now is Borel regular, and for any compact set K in Rn. So in Rn, we are very free to characterize the compact set. Which are the compact sets? The closed and bounded. Okay, for that measure is fine. Okay? For every compact set, whenever these two criteria is Borel regular, and for this we call this mu to be a radon. So one first observation was initial observation is just come that the Lebesgue measure we have defined for Rn is a radon. How? Because it is Borel regular, it is Lebesgue, so it is Borel, but not all Lebesgue is Borel, but all Borel is Lebesgue. What comment I have made here? Borel, and it is regular. Why it is regular? Because you can see that for a given set, you just make some epsilon with adjusting the side length using epsilon, and you will get a keyword just such that its volume is exactly same as that measure of that set. And for any compact set, as it is closed and bounded, so what happens? As it is bounded, that means its measure should be bounded, so it is finite. Okay, so this thing will work. So this is called the radon measure. So one example, Lebesgue measure. Lebesgue measure on Rn is a radon. This is an example. And why it is true, we can see. Oh. Now we have a proposition to how to generate a radon. So a measure Euclidean measure which is Borel regular on Rn. Suppose A is mu measurable and measure is finite, what we have that this we define. So check that is a radon. So basically what we have found from a just a Borel regular measure, we have found a radon measure. How? We have defined a new measure that mu restricted to A such that, so for a B we want a B set B and which is mu A intersection B. Now we can check that this mu restricted at A is a radon. So this is what we need, how we get a radon measure from a Borel regular measure, and then we can have certain properties in product measure. So there are two measures, one measure we have. So how we define its product or such things. Just defining shortly. So mu is a measure on X, mu is a measure on Y. Now mu cross mu is called the product measure, is from the power set of X cross Y, maybe a shorter collection for those sigma algebra. It is also a measure actually, and we define to be, what is this? To be infimum of I this. So it is the definition that how we have this, we get this measure. This is nothing but the infimum of this, where AIs are mu measurable and BIs are mu. So this is the simple thing what we have. And one comment on it I would like to make, that if A is mu measurable and B is mu measurable, then A cross B is mu cross mu, and one can show that this measure of this is exactly the multiplication of this, measure of this and measure of this. So it is a very famous theorem which is to be okay. That is the thing. Now what we do is that we just try to finish just putting a thing to our main theorem we want to do. Now what we have, that what is the LA? So L1 of A, it is just the one dimensional vector. this is the standard notation we use, not that new or that thing. It is okay, you can use it, but standard we use this notation, which is simply infimum of union of just make the same thing what we have. I have given as a definition of the more or less the same. Okay. Now just one observation that n-dimensional Leibniz is nothing but n. So how you can prove it? Now these are the one-dimensional Leibniz. Now use that theorem, that Fubini's theorem, and you will get that. After some time, you will get that this n-dimensional Leibniz is nothing. Okay. Okay. So this is what I want to tell about basic measure theory, which will be needed in some times here. Now we give the motivation of doing the covering theorems. So basically, what a covering theorem gives, that we have certain set in Rn, let's say, we will produce a cover of that, and our motive of doing that is to study of a particular function in that set. But whenever we have that cover, we have some more additional information to study the function and the fine properties of it. So in this regard, some covering theorem was, and studying, I will tell the name, but it's have very long description, that some maximal functions and so on, it often encounters in number theory and so on. To define those things, we need those covering theorems. Okay. So let us start with giving some primary definition, and we will go for okay. Now some notation. B is defined to be BXR. What is BXR? X is the center of the ball and R is the radius. It is in Rn. It is a ball. It is a closed ball. Closed ball with center X and radius R in R. This is our notation. And what is B hat? B hat is nothing but the center unit fixed, but radius becomes 5 units. This is our notation. So there is nothing. But observe one thing, that is a closed ball. First of all, it's closed ball, so its boundary is here itself, and it has a radius R, and it is in Rn. Let's move forward. And now definition. What I mean by of, I need to tell a collection script of closed ball is a cover of set Rn if okay, so when we tell it a cover for a given set A, if we have this condition, means in those collection we will move our balls, and using those balls I have this set theoretic inclusion. Then we tell that if this collection to be a cover of set A. So one can easily see that this cover is not unique. Okay. So further, I just this A is a fine cover, we call it a fine cover of A. It is first of all a cover of A, and so what we have, the fine cover, when we call it fine cover, it is a cover first of all, and it's the diameter of B, the infimum of the diameter of B is fine. Okay. So we call it a fine for all x. So this is the definition. Now we come our first most important theorem, which is called the Vitali covering theorem, but I will not give the total proof, I will just state it and move on to the Besicovitch theorem. But I will tell you where that Vitali covering theorem lacks, why we need that Besicovitch covering theorem. Okay? So this is the main motivation of doing Besicovitch covering. Let if in collection of non-degenerate closed balls. Now what do we mean by non-degenerate? It is not a point. It has some positive radius. In Rn with this thing, okay. So with what? Diameter of all this ball B, so ball diameter is nothing but the twice the radius, right, of all ball B from that collection, and take its all supremum, the supremum is fine. Okay, so this is the thing, and then there exists a countable family with G of So what this covering theorem states that F is a collection of non-degenerate balls in Rn with this condition. This condition is important. With this condition, then there exists in this collection we can find out a countable collection of balls, okay, such that this holds. Means the union of all those balls from this collection can be covered by some enlarged size ball from that countable collection. Okay. So this is the theory, but the proof is non-trivial. You need to do the proof, but I am not going to the proof because some time constraints. But here one thing you observe that here what we are doing actually, we are making, using this criteria, we are enlarging the ball. Okay, this B hat ball is enlarged ball. It is the 5 times the radius. Okay, we will enlarge the ball and somehow try to cover this. And how we cover? We make that collection. We justify that that collection is a countable collection. That's all. But here one thing just we have used, that we are enlarging balls. Now Besicovitch Covering Theorem, but this enlarging ball, it is 5 times R, it is fine. But whenever we study some fine properties on some set A, X or something, this enlarging, the process of doing this may fails, may don't give the optimal outputs whenever we study the analysis of those functions. So in that sense, what we do just basically we make use not use this enlargement, this 5 times the radius, but what we use some another trick, just moving around the centers and make a control over the number of balls it has, which is particularly the Besicovitch Covering Theorem tells. Here we have a countable collection. I don't know what is the collection. It may be an infinite collection. Okay? And it is also some enlarged ball, using some enlarged ball. So in that scenario, it is very useful to make this thing more precise by using the centers and making less overlaps. Here it overlaps. You can see that whenever we just certain have some ball in 3D, if you do like this, then one radius ball it will be covered by certain collection, okay, but the balls will be very huge and the total thing it will cover it very much than this actual that ball. Okay. So it is somehow it realizes us that it is not optimal. So we will try to optimalize this covering theorem. So here pops out the Besicovitch Covering Theorem, and I mentioned this. Okay. So the motivation, one line motivation I want to give that mu is Radon measure. On Rn. So there is to optimize the study of functions. This is the motivation what I have told you just now is just there. Now I write the distribution statement. Skip the proof and I will end. Here. With the same condition that supremum diameters and if the set of centers of balls F, then there exists a small countable collections G1, balls in this collection of A such that A is covered by okay. So what is this Besicovitch Covering Theorem tells? That we have a constant capital N just depending on the dimension, which is maybe R1, R2, R3, it will be 1, 2, 3, and so on. In just depending on the dimension, the small n, and it has the following properties. What? All the things what we have for Vitali is okay, fine, and the conditions. And if A is the set of centers of this ball, of those balls in M. So A is just the centers of those balls in this collection F. Then what we have? Then for this capital N small n, this is a countable collection. It will give this countable collection G1 up to Gn. This one false, such that this will cover all the centers will be covered. All the centers, yes, all the centers will be covered by that. And eventually, if we make all the centers to be covered, and if we just enlarge some little the ball, you will cover the whole space. Okay. So here, what we have a good control over the centers, because A is the set of centers of the balls in the collection A. We have the good control. So here this Besicovitch Covering Theorem is very much useful, whereas that Vitali was not. Vitali Covering Theorem was not that much powerful there. So I will not give the whole proof because the whole proof is huge. I just make some crucial steps or claims, or how I will just explain how it works, how to do it. Okay, so after that I will stop. So let us start. Now first our journey of the proof starts from A to the boundary. Taking A to the boundary. Okay. And we will consider another case where A is not bounded. Means what is meant by A to be bounded? That means A was the collection of the centers of that collection, balls from that collection. So it is bounded, first of all. Yes. And write B to be the suprema of B okay. We said this, and it is finite because of these assumptions. So B, I have control over B, which is not blowing up to infinity. Okay. Now we choose ball. Choose any ball B1 to be B of A1 tau 1, which is from this collection. We choose a ball, just the center is A1 and the radius is tau. Okay? Such that tau 1 is greater than or equal to 3 by 4 times B by 2. And we will inductively choose Bj's. B1 I have chosen. I will inductively choose Bj. How? Inductively choose Bj for bigger than or equal to 2. J's are A. What is Aj? Is this. We have B1, B2, and this is an induction process. You can check and choose Bj. We have now Aj. We choose Bj. Equal to B Aj Rj from this F collection, such that belongs to AJ belongs to this AJ and RJ is greater than 3/4 of the suprema of R of R is F collection and A belongs to. So this is a clever way to choose the radius. The center will come from this set A minus this union up to J minus 1, and the radius I have chosen a clever way such that it's 3/4 the supremum of the all possible balls whose centers are in AJ, and that balls should be lying in the collection the F. Okay, we have cleverly chosen. So now first plane. Okay. Now what thing can happen? I just write if AJ is non-empty, it is possible that AJ is empty, but it is possible that AJ is non-empty for all J, and we set J to be infinity. Okay, and our first claim here I write. Claim that if J greater than I, then Rj will have this. Okay, you should check it. It is nothing but use of the definition. That definition and this. Just use this and you will get that if J is greater than I, then this Rj will be less than 4/3 of R. Okay. Okay. Now claim another claim that the balls B A J also you use the just distance argument from the sentence. Okay, just take two of the balls, means AI and AJ, and or yes AI and AJ, and you give some condition from AI minus AJ. Okay, if there is two balls, when it is disjoint, this total thing should be greater than each of the radius, summation of each of the radius. So using this argument, you can put this selection. You pick any two and use this claim 2, claim 1, and you will prove that this will be true. So then you will directly claim that yeah, it's this. So then the claim will be done. And now what we have considered, that we have set J to be infinity. Now another claim that J equal to infinity, that implies limit infinity Rj. So what it means? If that condition holds, if we have these things, now whenever this J is infinity, means J is huge, then the balls, by how we are constructing, the ball is shrinking. If you observe crudely, that you can see that the ball is shrinking. The ball is becoming smaller and smaller. So this thing will come. You can prove it. It's also check by using of this thing. They are all disjoint. using radius. So they are all disjoint and you are feeling that. So radius must be small. So it's an intuitive idea, but it is just from this. And another claim. That A is subset of this connection. How? This is just because of this construct. We are taking all bi's and just we subtract it from A and we are taking AJ and we are covering certain edges using the centers and with the radius and certain edges. And whenever we union all those bj's, these bj's, it will cover. And now we define a set. For k greater than 1, let I define j's So what is I? It is the collection of j's, small j's, such that this is disjoint. Okay. Actually we are optimizing. So A is covered by that all the collection B1, B2 and j's, and we are taking the I to be the j's for which they are disjoint. Not disjoint, sorry, which are not disjoint. So our goal now is we have to take a control over that capital J such that that thing which is inside the code, that A will be inside some countable collections of G's, and depending on those, that capital N small n, it's depending on the dimension of this N. So our goal is to estimate cardinality of whenever we will estimate the cardinality of I, then we will come to know that how many BI balls, these balls are not these two. Okay, and then we will proceed. Okay. Set K to be capital K to be I intersection is such that so this K is what is this collection, this set I, and the intersection with wherever Rj is less than equal to 3 Rk. Okay, so Rk is from where? AK. This ball AK and Rk. AK is the center, Rk is the radius. The ball inside that A, the center is at inside AK. Okay, we have this collection. So this intersection we set only K. Okay. Now we can prove that. Check that cardinality of this set K how do we prove that? We just use for a particular x and AK from capital AK, we can show that this is just less than equal to 5 Rk. Okay, for x belongs to that Aj comma Rj by 3, what we have defined earlier. Okay, so these sets are disjoint. We have the claim. Okay, and we will use that thing, the fact that that will imply we have enlarged the radius of 5 times. We can prove that this will be this, and then in that case it will be and we have this, and from claim 2 what we have, these balls are disjoint, and what we have that so Ln, the dimension of the vector is of the I by A is less than equal to this direction due to the non-chronicity of the result, what I have to do the beginning. And this is just a scaling factor, so it can be out, and it's 5 to the power n factor will come, and wherever we have Rj by 3, this factor can be controlled using that first plane. Okay, that first plane. So Rk by 4, this will be controlled by Rk by 4, and it is also 1 by 4 is a scaling factor. Then you pull it out, 1 by 4 to the power n, and we multiply here, so it is to the power n, and this these and these will be equal. It will be cancelled out, and just number of edges, the number of balls in this collection, this summation is the collection. So it will be the K, which is our K. So this cardinality of K, that will be n. So J's are moving in K. So here we will make it Rk by 4. 1 by 4 factor will come out, and its n dimension 1 by 4 to the power n will be there. From here it will be 1 by 5 to the power n from this. Now observe that this will be same as those balls, but the number of ball is the cardinality times cardinality of K. So volume of those level measure of those balls is equal to the cardinality of K into a particular ball, AKRK, and it is the same here, so it will be cancelled out, and as these were non-linear, you can cancel it out. So what remains is the cardinality of A is which is less than equal to 5 to the power n and 4. So it is 22. This is our proof of the claim. Now, what to remain? We want to estimate I. What we have estimated is K. Now we will estimate the cardinality of I minus K. If we add those two, we will get the estimate for I. We have made the estimate for complement set, and that set it will give the whole. Okay. That is the our way of. And there what we have in summary, and this and what is this dy and dk is not 5, so not disjoint, and also dj intersection dk. That means if you have this wall and another wall is cutting this. These are not two disjoint. This is the dj wall. This is the 3i wall. Sector is AI. Sector is AJ and it's and the angle. Oh, so you can translate it. And without loss of geometry, you can take negative at the origin. The total setup will translate to origin. And the mirror is not maybe singularly under translation, so it will not make any problem. So we take these two vectors because we are in Rn and we have this angle. Okay. Now with some geometric facts. Some geometric facts. From here you can derive it that 3rk is less than ri, less than this length, less than equal to ri plus rk. We have and 3rj less than rj, aj, these three facts you can just derive using all the conditions that this is not disjoint, this is not disjoint, this is not disjoint, and this, and the theta is the angle between this, and certainly this one is dk, it is intersection this, it is not actually both di and dj are intersection. So here now what we do, we have some geometric thing to certain bound for theta. So what we are trying to do, we making the overlaps less. So we have to make some bounds on theta. Okay. Theta is greater than 5/6, then AI will be inside dj if cos theta is greater than 5/6. The proof is very easy using cosine 2. So suppose and from the cosine proof that cos theta will be just what is cos theta from here you can just derive. And use this property, you will get that that implies that will imply. You just use this one. Okay. And another claim that if AI belongs to Bj, we have some upper bound like that 0 is less than AI minus Aj plus AI minus Aj and Aj times A equal to 1. This is also from cosine rule and certain triangle inequality. This part is okay, this part is not the issue, but is greater than 1. But for the cosine rule, you need to use some certain manipulations, and you will get finally this. Now another claim, we have this bound. First one is just by triangle inequality, and later one is using some and then if AI belongs to Bj, then cos theta that is the thing. Whenever this holds, yeah, cos theta is greater than 5 by 6 for AI to be in Bj, but whenever AI is inside, not inside Bj, we will have cos theta is less than equal to. Yeah, this is the opposite state. Yeah, cos theta is greater than 5. Okay. Now here we estimate cos theta that it is less than equal to 61. Okay. Basically what? For if cos theta is greater than 5 by 6, then AI belongs to Bj. Now what we have, whenever AI is not inside Bj, then we will show that cos theta is less than equal to 5. It is the same, it's the contraposition. Okay. Oh. So now what we have, that from that thing, last line that I have written, and we have, since AI belongs to Bj for that thing and Aj not belongs to Bi, we have Ri Aj less than Rj. It is from geometry. You can see that AI is in Bj and Aj is not inside Bi, then it will be greater than the radius of Bi. This is the Ri, and this is less than. So, and I is less than J, and what we have previously in the first, right? And from there you can conclude AI minus Aj plus AI minus Aj. This thing is greater than 1 by 8. Okay, is the thing. And from there you can have, it is not 0. Here it is, I have a good block, this 1 by 8 Aj for here. So ultimately it will be 1 by 8 AJ AJ and AJ that equals 1 minus. Now you take these two sides and conclude readily. This side and this AJ will cancel out and you will get cos theta less than equal to 6. So I am just going to finish the proof that for the claim for all I comma j belongs to this set I j is not equal to I is not equal to j theta belongs angle between here minus AJ and AJ minus AJ. Then theta is less than equal to cos inverse so it is just obvious from previous. We have a bound for theta, that's the whenever AI belongs to Bj. Now you just take another bit as AK and you just make AK to AI and AK to AJ and you will see that this the claims that okay. So final claim our final claim and then some set theoretic argument will come to the proof that the dimension that partial area of I minus k. So fix are not to be greater than 0 and such that x belongs to the boundary of the ball, that x one radius ball and yz belongs to dx r naught. Now from claim 6 we can choose ln such so that that boundary can be covered. Okay, these are very good technique to cover the. We just cover the boundary, and we will make the radius little bit larger, and it will cover the whole ball. This is a simple trick we need to play. this here will be covered by Ln walls. The boundary. On the boundary we have the points, the centers, and on that centers we have just enlarging the ball and it will cover the ball. But this is the optimal bound we are claiming, because if we just decrease it by 1, it will not. This is the thing. And finally So how this that kth decay ball, this is b delta t1 and for some b is okay, so it will be covered by the same boundary point on the boundary, but the radius will be scaled up r0 into rk, okay, and with centers on the boundary. Now from the claim, that previous claim, there from this claim what we have, that this angle cannot exceed 61/4. Okay, this AI, the angle between AI minus AK and AJ minus AK can't exceed the 61/4. Okay, so this implies previous claim implies that AJ minus AK and AI minus AK cannot both go through the same ball. Hence, this cardinality now we are almost done. Cardinality of I is cardinality of A and cardinality of I minus is nothing but which is vector. Call it now we just want to give the family of sets, that G1, Gn or Gn in. So for that we have some notion of permutation, that we define a collection families of disjoint balls, define sigma from this around the set. Let sigma I is I for and for k greater than equal to n, we inductively define sigma k plus 1 according to the calculation and we define this Gj, that first one, the walls sigma. This is our okay. So from here you can easily see that according to all the construction we have made, that A was inside this. One, A, which is nothing but 11. We have constructed the things and it was all those for this one and which is same as this, but we have a control over how this GI, this countable family will look like. In Vitali it was not there. Now this is for this is end of the proof, that for what we have A to be bounded, the collection of the center to be bounded is okay. Now for A to be unbounded, what we do for this is sorry. That was A. For small greater than equal to 1, let A be the A intersection x, B is -1, B is our previously introduced B, x, B, and how would we define the collection? If L will be the collection of all balls such that so from the last step here we have made it the AL to be smaller and making A is unbounded, but we are making ALs to be some certain bounded. But for that bounded thing we have to like this. We have this thing and we have that exists countable collections. Such that subset of union so for each AL we have the bounded thing is here and we will make use of A using AL and finally we get that is A Just one final comment I want to make. Stop. That consequence suggests we can get sample collection of balls is instead of a open set. In the place of open set, we can get a countable collection of disjoint doors instead of open set, such that the part which is not covered, like this part, small part that remains in part as a measure. It is somehow optimal. Maybe we get another finer thing, but using Besicovitch Covering Theorem, it suggests that we give an open set in Rn. I can cover it, or somehow I can pack it using collection of open sets, balls. Maybe they are always disjoint, such that this collection will be countable, but the remaining part which remain to be filled the total open set will be just a set of results. So I don't care on that remaining part, because in that result zero set, how the function behaves, I don't bother. I want to bother in a certain set where there is some positive. Otherwise, in the result zero set, how the function matters is we doesn't really care. So here I end my talk.